All right, let's do some mathematics then. Section 4.2, probability. We talked about 3 general techniques on how to calculate or estimate a probability. Can someone impress me with their memory and tell me what those 3 are? Okay, you have to be louder.
Reactive, frequency, classical approach, and conjective odds.
We have the frequency approach with relative frequency. When do I use a relative frequency approach to estimate or approximate a probability? Give me an example. Yes.
Tossing a coin.
Tossing a coin, and how would I do that?
Well, the more times that you toss the coin, the higher the closer your probability is going to get to the actual probability.
You're stealing my thunder. That's the next topic, the law of large numbers. But he's exactly right. If I had a suspect coin and I didn't know whether it was fair or not, I could toss it 100 times and count the number of heads, and that percentage of heads I could treat as my approximation to its probability of the heads. That's relative frequency. All right? If I wanted to use a classical approach, there's one key assumption that has to be true, and that is what?
All the outcomes must be equally likely.
Yes, all outcomes must be equally likely. So I can use that approach when I'm flipping coins or counting boys or girls in bursts, because for our purposes, those are equally likely. Okay, let's push ahead here then. And Wrights gave me this nice overview to talk about the law of large numbers. I don't know why we call it a law, or just a theory of mathematics, but I guess it gives it extra weight. Reading through the words, it's probably not real clear what's going on here, is it? That's what it is. But let me show you an example of what it means. I think it'll, and then go back and read the words again, and it'll make sense. And I'll have a little John after. Let's take this example. Let's suppose I had a coin and it was suspect. I didn't know it was fair or not. And I wanted you to come up with the probability, your approximation or your estimate of the probability of getting ahead when I flip this coin. So what would you do? Well, you start tossing it. After each toss, I could calculate the relative frequencies of heads that I had so far. Toss it once, and on the second column, I gave us a string of results. We're pretending those are the results. The first time I got a head, I've got 1 head out of 1, so my relative frequency is 1. At that point in time, what's my estimate of the probability of getting ahead? I don't know any better. I toss it again, and I get a second head. My relative frequency is 1. Then I get 1 tail, so I have 2 out of 3 heads. And you can see the pattern. As I do this more and more often, is there any guarantee that these numbers will actually converge to the true probability? That's the question behind the law of large numbers. You can see at first they bounce around a lot, don't they? Is there any guarantee that I do this 100 times, 1,000 times, 1,000,000 times, that I will get really, really close to the true probability? Oh, yes, there is a guarantee. It's the law of large numbers. This example is just what these English sentences mean. If you calculate a relative frequency enough times, then you're guaranteed you'll get close. And we're using air quotes here, enough times, quotes, to the real probability. That's the justification really for using this technique. Otherwise, if I couldn't be guaranteed, why would I use it? That's a pretty deep theory in math. We're not going to try to prove it, but we're going to make use of it. And there's a little Java applet I thought that was, this is it. we're going to roll dice. Gambling is a huge part of this course. Now, this is a simulation, and behind the scenes, they're random number generators. They're programs that, if you tell them, I want to simulate a roll of the dice, it picks a random number between 1 and 6, and all of the numbers are equally likely. So we can tell it how many times we want it to roll the dice, and it's going to plot here the average of the number that appears, the number of dots. Okay, the dice has 1 to 6 dots, so over a long period of time, what do you think would be the average, the number of dots that appear? 3. Makes sense, right? All right, this is the law of large numbers at work. We're rolling it 10 times, simulating it. And we started out, you can see how it goes up and down a lot. It's not exactly relative frequency, but it's similar to it. I'm doing a count, a mean, keeping track of the mean number of dots that appear. Well, that was after 10 rolls. Let's go ahead and roll it 100 times. And what the law of large numbers is telling us is we should expect to see the ups and downs become smaller, and it's going to converge closer and closer to the true value, which is 3. We know that. And if you have the time and inclination, you can tell it to do 100,000 rolls, 1,000,000 rolls, and so on, if that's entertaining to you. But that, in a sense, that's the law of large numbers. All right, next on our agenda, today's we're going over a number of definitions and concepts. Then I have some problems we're going to work on. We'll post class with a worksheet and have you work on problems for 15 minutes or so. An important concept, a very simple one, but surprisingly valuable. We know we define what events are. We've done lots of examples of those. And we create sample spaces, haven't we? A sample space is a set that's all the possible outcomes of my procedure. And we know an event consists of 0, 1, or more of those outcomes. Well, now we say, if that's my event, what's everything else that's left? And we're going to give that everything else that's left a name. We're going to call it the complement. So A is my event, A bar, or the complement of A, consists of all outcomes in which the event A does not occur. So if I take A and its complement together, I have everything, don't I? I have the entire sample space. Let's just pause a minute and a simple example. We did the boy, it's just two births. Boy, girl, boy, boy, girl, boy, boy, boy. That's my total sample space, 4 possible outcomes. If this corresponds to my event, say at least one boy, wait a minute, I need a girl here, don't I? That would correspond to the event at least one boy. Well, what's the complement of that event? Well, it's everything else in the sample space. In this case, it would be that would be E bar, the complement. Now, from that simple observation, you can come up with this formula, again, deceptively easy, that says the probability of an event plus the probability of its complement has to equal 1. You see how that makes sense? We define the probability of 1 to be certainty, isn't it? It's absolutely guaranteed that this is going to happen. So what we're saying is, if you execute your procedure, we are guaranteed that either you're going to get something from the event or it's complement. That's a sure bet, isn't it? Because there isn't anything else. Now this little formula is going to be very handy. We're going to use it later on to solve some problems that would be pretty nasty if we didn't have it. It's surprising how something that simple can be very useful. So keep it in mind. In particular, the value is, I can write it three different ways. P of E plus P of E bar equals 1. Or I can shuffle things around and solve for either P of E, that's just 1 minus the probability of its complement, or I can solve for the probability of the complement, and it's 1 minus the probability of the event. Now this isn't college mathematics here, this is pretty straightforward algebra. What's the big deal? Well, it turns out there are situations where it's really, really hard to calculate the probability of an event, but it's much easier to calculate the probability of its complement. And we're going to do one of those in a couple classes that I think will astound you. We're going to do the classic birthday problem. So we'll keep this in mind, and this is going to be very handy at times to calculate probabilities that otherwise would be really difficult. I can just look at the problem the other way, and maybe I want the probability of the complement, I look at the probability of the event, or if I want the probability of the event, and I find the probability of its complement. So with that in mind, you need to get some practice of this concept of complement. Here's the first example. We survey 110 people and we find that 202 are smokers. So using the relative frequency definition of probability, the probability of a smoker is just that relative frequency, 0.2. So my event, E now, is the person's a smoker. What's the complement? Well, you're not a smoker. And those two probabilities have to add up to 1. So if I know this probability, I can quickly get that probability. Let's practice identifying what complements are. Next president of the United States will be from Virginia. Lombardi, what's the complement? Griffin?
Meaning the president can come from one of the other 4 United States.
Exactly. There's at least one boy in 3 consecutive births. Charco, what's the complement? At least one boy.
So any of the combinations that didn't have at least one boy.
All right, we can say that even more concisely. Complement of at least one is always going to be
1 out of 3.
let's write them down. It takes a little while here. Make sure I don't miss one. We've got boy, 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 girl, boy, girl, boy, girl, boy, boy. All right. Then we have girl, 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 boy. Did I? Which one did I miss?
Boy, girl, girl.
You have that one first.
Boy, girl, girl?
No, I think there are only
It's gotta be
2, 4, 6, 8.
Okay.
So what are all the events, what are all the outcomes that satisfy the event at least one boy?
Well, all of them.
Yeah. What's the complement of at least one boy? All girls or no boys. Complement of at least one is none. And that's a handy fact because we're going to get a lot of problems that have at least in them. Whenever you see that, think about taking the complement and finding its probability. That's a verbal clue that's going to come up a lot. How about at most one boy? Got done?
Anything with more than one boy?
Sure, in this case, if it's at most one boy, it would be, that's got one boy, that's got one boy, that's got one boy. That has 3, 2, 2, 2. So that would be the vent, that's the complement. A randomly selected cadet is a member of the first class.
Second, third, or
Second, third, or fourth, however you want to refer to yourself. A selected cadet has green eyes. Cadet Hamilton?
That doesn't have green eyes.
So whatever our list of eye colors are, we say they're green, brown, blue, all those that are not green. 4 coin tosses results in 3 consecutive heads. Is that right?
The one that is tails.
This is a little bit harder to say. I'm not going to try to write out all of these, but our event is 3 consecutive heads, so the complement would be any string of 4 coin tosses that does not have 3 consecutive heads. And I don't know any easier way to say that, but that is what it is. All right, a little bit of practice doing that. Those are the answers. Now a little housekeeping chore here. When you express probabilities, and the stat lab exercises enforce this, or reinforce it. Well, we have this really handy little equation that we use a lot, the classic rule, P of E equals S over N. So we end up with fractions. Now, I know fractions are not popular nowadays. In the old days, we liked fractions. I like fractions. If you get something like 1/3, that's a legit probability, and on a quiz or test, you can stop right there. If you feel compelled or the need arises to express it in decimals, we're going to use 3 significant digits. And that's going to be our standard, and I'll put that in all quizzes or tests is what I'll expect to see from you. Now, a quick refresher, 3 significant digits. How many significant digits in this number?
1.
Good, Bobby?
like 3, I guess. Let's go 1.
What do you ignore when you look at significant digits? Yeah, leading zeros. This is really a placeholder. That has 1 significant digit. That has 2. That has 3 significant digits. That has 3 significant digits. All right? Get the picture? Basically, we ignore leading zeros because they're just there to tell us where the decimal point goes. All right. Fasten your seatbelts.
Sir, I just have a question.
Sure.
The 0 is between 2 other numbers that are significant. Does that make it significant?
The author in this edition changed terminology slightly. And I find it challenging because we're taking 2 words in the English language, unlikely and unusual, which are usually synonyms. And we're kind of getting a razor out and saying, no, they're different. All right, here's how they're going to be different for us. I'm not sure this is common throughout statistics, but we'll go with it. It's with our book. Event is unlikely if the probability of exactly that event happening is less than 0.05 or 5%. And here the key distinction is the probability of that event. Now, this is the one that's troublesome. an event is unusual or has an unusually low number of outcomes if it is not within the expected or usual range. Let me go to an example. Help us out with this. We'll go back to our good old trusty coin flipping. My procedure is to flip a coin 100 times and count the number of hits. What's the probability of getting exactly 55 hits? Well, as of now, you don't know how to calculate that, or we haven't gone over it. But we will shortly. And it's actually 0.048. It's not very likely. And if that surprises you, you're thinking, well, 55 is close to 50, I think it would be a higher probability. Keep in mind, if you're flipping a coin 100 times, there are 100 different possible outcomes. Anywhere from 0 heads to 100 heads. The probability of any particular outcome is quite small in this case, because I have so many outcomes. A specific outcome is unlikely. This is unlikely. Is it unusual? Well, now we look at not just the probability of this event, but we're looking at is it within the usual range of outcomes? So let's go back to our range rule of thumb. Remember how we determine whether outcomes are usual or unusual? By using a mean and a standard deviation. Now, I will tell you that for this experiment, the mean is 50 heads and the standard deviation is 5 heads. Again, that's something that we will learn in a couple weeks. But given that that's the mean and the standard deviation, is 55 an unusual number of hits? The test wasn't that long ago. Why isn't it?
Because it's within one standard deviation rather than two.
Excellent, yes. Within we said plus or minus 2 standard deviations would be the range of usual values. So 50 plus 2 times 5, that would be 60. And over on the right-hand side, and on the left-hand side, we have 50 minus 2 sigma. And we would say that's the usual range, or roughly 95% of the times, when I flip a coin 100 times, I'll get heads between 40 and 60. Now, with that meaning, is 55 heads unusual? No, it's not unusual. Is it unlikely? Yes. I know. We're splitting hairs in the English language here, but that's how we're going to interpret it. Unlikely, you're looking at just that event, and usually taking the big picture and saying, am I surprised that I got that? And you'd use something like the range rule of thumb to say, you know, that's a pretty typical result. Well, Stat Lab will give you some more practice on that. Okay, a variety of topics today. Odds. Odds for and against. You've heard this expression a lot. In the Super Bowl, there's always the Las Vegas line, you know, the odds for San Francisco were, or the odds against Baltimore were, or when they have the Kentucky Derby, you have all the odds for a particular horse, 5 to 2, 3 to 4, something like that. What do they mean? Well, it's pretty straightforward. A is our event. So you're always talking about the odds for this event happening or the odds against it happening. I have the event and then I have its complement. In the common usage of it, the event would be the Ravens win, the complement, the Ravens don't win. Or the event is a particular horse wins, or that particular horse does not win. if you're looking at the odds against, the way to remember this, I'm betting against the event. So that is the ratio of two probabilities. On the top goes the complement, and on the bottom is the probability of just the event itself. So if I'm calculating odds against, put the probability of the complement on the top. If I'm calculating the odds for, then I'm looking at a ratio of the odds that A will happen divided by the odds that A will not happen. And the way we typically write that is not as a fraction or as a decimal, but we just we write those as a colon in between. Now let's do an example. A roulette wheel has, so I'm told, I've never played roulette, 38 slots. So if you're betting, one of the bets you can make is on a number. And each slot has a unique number. It also has colors. There's lots of complex ways you can lose your money. But one of the ways you can lose your money is by betting on a number. So A equals the event that 13 occurs. You bet on 13. The complement of A then is, well, so you win. And the complement is you lost. And in the set down here is all the numbers, all the outcomes on the roulette wheel except 13. I think there's a 0 and a double 0 and it goes on and on. All right? So what are your odds against winning? Well, I need to know two probabilities. I need to know the probability of the event and the probability of its complement. What's the probability of your event, meaning 13 came up in the slot? 38 slots. We're using the classical approach because we're assuming it's a fair roulette wheel and all outcomes are equally likely. We hope that's the case. So that would be 138, wouldn't it? And what's the probability of the complement? Well, it's 1 minus that. It's 37 out of 38. You've got 37 ways to lose and 1 way to win. So what are your odds against? Well, against, we put the complement on the top and the event on the bottom. And that would be 37 over 38. And on the bottom, 1 over 38. And that can be simplified to 37 over 1. And the way I would write that, 37 colon 1, and we'd say the odds against are 37 to 1. Which just means the probability that you lose is 37 times greater than the probability that you win. Okay, what's the probability for? Well, that's the probability that the event's going to actually happen. So in that ratio, we put that probability, P of A on the top, and on the bottom, we put the probability as complement. And now I just have this flipped, don't I? I have 1 out of 38 in the top and 37 out of 38 on the bottom. And that would be reduced to 1 over 37, and I'd write that as 1 to 37. Which is saying the odds you're going to lose are 37 times bigger than the odds you're going to win. Okay, I'm going to hand out a worksheet in a little bit to give you some practice of doing this. Did that, did that. Okay, well, let's do these as a class, then I'll hand out the worksheet. We're gonna roll the dice, and I'm going to observe the number of dots on the top. That's my event E. What is the probability that E is an even number? Let's see. Who haven't I given opportunity today? Yeah, Dylan? Let's start at the basics, all right? What's my sample space look like? So what are all my possible outcomes? If I roll the dice and count the number of dots,
Yeah, 6 multiple outcomes.
and they're just the first 6 integers, right? Okay, now what's P of E? Well, before I jump to that, let me ask you another question. Are all these outcomes equally likely? If it's a fair dice? Yes. Now, why did I ask that question? Who cares? Why did I ask that question?
So we can use the classical.
If that's the case, I can use the classical approach. And that probability, P of E equals S over N. What's N? Excellent. Yeah, it's the total number in my output, my outcome space. So that's 6. What's S? It's the number of outcomes that satisfy the event. My event is E is an equal number. Okay, there's your list of outcomes. How many of those satisfy that event? 3. Now, this is a simple problem, but if you go through these step by step, this will serve you well. If you can identify your sample space, that's great. Then the next question you want to ask yourself, are all these outcomes equally likely? If they are, then you know, oh, I can use the classical approach. How about the next one, probability of E less than 5? Yes, your turn.
Probably less than 5,
I still have 6 outcomes, and how many of those are less than 5? 4. How about the last one, the probability that's a prime number? Okay. 3? Little aside number theory. How many of those numbers are prime? 4? Well, there's one even number that's prime, 2. We throw that in, then 3 and 5. So that'd be 3 over 6. No. We don't go there. All right. A bag contains 12 marbles. That distribution. What's the probability that I select one at random and I get a red? Roscoe? First probability. What's the probability of a red?
It would be 3 out of 12, 1/4.
You know, what assumption is he making when he did that calculation? It's correct.
That every marble has an equal chance.
Yeah, equally likely outcomes. And if I'm grabbing into a bag and I'm not peeking, the bag shook up so the marbles were distributed, reasonable enough. You're going back to P of E equals S over N, and that's just 3 out of, what's the total, 12? Yes. Okay. What's the probability of the complement of that event? Quickly.
9 out of 12.
P of E complement is 3/4. You know that without even pausing because it's 1 minus that. And what are the odds against selecting a red mark? Okay, now what do I need to calculate this? My E is select a red. So I need P of E. What is that equal to? Did you do that already? That was 3/12, wasn't it? Or 1/4? And I need to know the probability of the complement of that event. So that's 3/4. And odds against selecting it. Well, that would be complement on top and the event on the bottom. And that would be 3/4, 1/4, or 3-to-1. All right, we're getting the hang of this? Okay, here's what we're going to do for the rest of the class. I'm going to hand out a worksheet. This is not a work for grade. You don't have to hand it in. The answers are up an angel. I want you to work. First, I'd suggest